So we've been talking about the network layer for some time now, and what I'm going to talk about today is one of the most important services provided by the network layer, which is routing. So I'm going to go back and give you like an overview of what the internet looks like at sort of the nodes and edges, the graph abstraction layer. And we talk about two particular routing algorithms that are widely used. One is called the link state algorithm, other is called the distance vector algorithm. And both allow you to compute routes, which is a way of deciding which way to go. So you come to a crossroads, you can go left or right or straight, and routing is deciding how to do that. And then we'll look at two specific routing algorithms used in the internet today, Ospf, which is used inside a campus like Waterloo uses it, and BGP, which is what we use to kind of route across different networks. So anyway, all of this stuff will make sense once we start looking at it in a bit more detail. So let me do that. Okay. So I need my colored chalk here. So I'm going to start once again with the same picture that we've looked at several times now, which is sort of the bird's eye view of the internet. So I'm going to start here. So we have some end device. It could be like a laptop or a mobile phone or a desktop. And they're all connected either to a wired hub, okay, and you've all seen what those look like, or the same devices, a laptop or a mobile, could be connected wirelessly to some access point. And I should add that starting with the next lecture, I'll be talking about the link layer. The link layer is going to talk in much more detail about what happens sort of over here and over here, what happens in wireless, what happens over here. And if you have a cell phone which is, connected to some kind of cell phone tower, how does that work? We'll talk about that, those three things, starting in the next three lectures. One lecture will be on the Ethernet, one will be on Wi-Fi, one will be on cell phones. So we'll cover that in some more detail. But for now, we're going to kind of ignore the link technology, as it were, and just look at this over here. And they all go to essentially some kind of router. And these routers are connected to other switches and access points as well. So for example, this Ethernet drop over here, this wire over here, as I mentioned earlier, this wire goes into a wiring closet, which is somewhere in this hallway over here. And in that hallway, we have hubs, which are connected to these endpoints. And those are connected to routers. There's, I think, one on each floor of this building. And these routers go to some kind of router for math, so the MC router. And there are other routers as well. There's one in Davis Center. There's one router in, let's say, in biology. Okay? And these routers all connect to actually two campus routers. And we have two of them just because in case one goes down, we don't want to have, the whole system go down. So we typically connect them in two links, like so. And this is a standard kind of thing. And then these guys talk to each other to maintain what's called routing state. We'll talk about that in a moment. And this campus router is connected. These campus routers actually both connected to different providers. Okay? And if you remember the first assignment, you had this, I asked you to look at the AS. So an AS is an autonomous system. It basically stands for a network. Okay, so another term for a network. So what I'm going to draw here is the Waterloo autonomous system, which is this thing and this big circle over here. Okay. So this is the UW AS, whatever 12. Do you remember this AS number? 12093, something like that, whatever it is. I'll just make it up. Okay, that's UW autonomous system. All right, and it has roughly about 50,000 endpoints over here. Okay, maybe more, maybe a little bit more, maybe a little bit less. How did I come in 50,000? There are about 25,000 students, roughly 25,000, 30,000 students, plus employees, and everybody has one or two endpoints. So you get about 50,000. So so that's what's over here. The interesting thing is they all share the same prefix, 129.97.0.0/16. So they all share that prefix, and as you'll see in a minute, that's very important. Now what I'm going to do is that I'm going to draw a couple of smaller circles inside this. And so this one over here, this orange one over here, is sort of math, as you can see over here. All right, and then Davis Center has its own set of switches and routers and stuff like that hanging off of it, which I'm not going to draw. And let's give that green, so let's give that a ring like that. Okay, and then similarly biology, and similarly all the others are going to be like that. Okay. These things have a name, and this is called it's called an area. Okay, and this is an area as well. Now the other word we use for it is subnet. Okay, there's a slight difference between the two. It's not important for you to know the difference. We can call it area, you can call it a subnet, and I guess the difference is that the area can have multiple subnets. For now, we'll just assume each area is one subnet. And so this is the set of IP addresses which are all going to be in math, okay, in the math building, okay? And they would be basically 129.97. something, let's say 64.0/24 plus others, okay, which we don't want to go into. And similarly, this area has some list of subnets like 129.97.75.0/24 and 64.0/24. I think these two belong to DC and so on. So there's a list of subnets that belong to each of them. And so we can associate with each area a list of subnets, but for now we'll assume that every area has just one subnet belonging to it. Okay? All right, so what have I said so far? Well, we know this kind of structure over here, but we can kind of abstract it all out into notion of an area. And from our perspective, all that matters to the area is that it has one or more subnets which are aggregate IP addresses with the slash notation. Okay, so now we can move one more step up into the hierarchy, and this over here is our ISP. So we have some ISP A, and there's some ISP B, and we actually know what these are. This is Orion, and I think the other one was it Cogent? Who's the other provider? Cogent, yeah. Those are the two ISPs that provide service to Waterloo. Beg your pardon, Hydro One. Yeah, maybe that's right. Cogent was further up. Hydro One, yeah, Hydro One, right? They provide both electricity. They provide both electrons and bits to us. Okay, we better be nice to them. Hydro One. Okay, so so we have these ISPs, and if you spend any time looking at the AS map in the AS browser, you will note that these guys are connected to other ISPs, like so. And then let me use AS to be consistent over here. So AS something here, it's connected. And these guys actually have connections to other networks, which I'm drawing in pink. Okay, and so on, like so. And if I take the same picture and I kind of do a mirror image of it on the other side, that's how it looks sort of on the other side, whatever the other side is. Just to give you a sense of that, I'm going to actually not draw the other side. We're going to show you what happens when you go into a data center. And I think I did that in the first class, but I'm going to show it again just because it's relevant here. So let me break into one of these networks over here. I'm going to look at the Google data center in Toronto. So let's say it's connected to Cogent. I'm just going to pick the name out of a hat. And this is going to be connected to the data center network. Okay, and the data center network actually will have connections from two routers to two different providers. Same reason, we don't want these to go down, so we'll connect to two different routers, two different providers like so. And then these are connected to a bunch of what are called top of rack switches, as Andy had explained to you. These are the top of rack switches. Actually, the aggregation switches going to top of rack switches, and those go into the servers, the other servers over here. Okay, and so on. All right, and they all will share some prefix. Let's just say 128.32.0/16, just to put some number down there. Okay, so we've got this topology, and we want to ask the following question: how do we get from here to there? Okay, it's pretty straightforward. How do I get from? So I have this computer, which is my desktop over here, and I want to get to one of these servers at Google, let's say this one, which has, my Google Doc on it or something like that. How do I get from here to there? And so what I have to do is basically make a choice of paths, because there are actually many paths, right? Let me draw one sample path through here. So it turns out that for reasons of economics, we are never going to have alternate paths, or very unlikely to have alternate paths in the area. Okay, the area is kind of going to be mostly a tree. Okay, alternate paths cost money, and we don't want to spend that kind of money, because if I get disconnected, well, no big deal. I'll be disconnected for a while. It's not a problem. So we usually don't have alternate paths over here. You just have the single paths in orange going up to the MC router. So this is all single path. Over here, I have a choice of campus routers. I got to figure out where to go. And let's say I pick this one. I'll show you in a minute why. And then here, I really do have a choice. I can go this way or this way. And I'm going to draw one particular path. And we'll see in a minute why we chose this path. So this orange path is the one I chose, but I have very many choices. I could have gone up like this, and then over, and then down this way, and then back down like this, for example. Okay, I could have done that. Okay, why would I not do that? It's longer, right? It's longer, so adds delay. It also, costs more electricity. If you wish to minimize electricity costs, you don't want to do that. So that's not a good idea. So we have some notion that some paths are better than others, but it might turn out that this is a very high capacity path, this is a high capacity path, that's a high capacity path, and this is not a high capacity path. In which case, I probably want to go on what looks like a longer path in terms of distance, but is faster, lower delay, because I don't have queues, I don't have congestions. Okay. It's just like saying that the shortest path on the road from here to Toronto may be on Route 7, geographically, but it's faster to go on the 401 and go back up again because it's a freeway, it's faster. Okay, so we have that one. Okay, so this is what it looks like, reality, okay? What we want to do is to build a model for it. We want to build a model for it, meaning that we want to write it down in a way where it's easy for us to see how to make routing decisions, okay? Choosing this way or that way, okay? And that's the basis of routing, okay? So the first thing you have to realize is that reality is pretty complicated. Actually, there's lots more detail that I've left out of here that's going on. There's many other things that are in the way: firewalls and load balancers and proxies and caching hierarchies and who knows what, okay? But I've left it all out. What I want to focus on instead is this really simple-minded view, and we've actually seen this already, which is the graph abstraction. And I'm going to show the graph abstraction at two different levels. One graph abstraction is inside the UW autonomous system, okay? In this UWAS, I have these areas, as you can see over here, and I can draw each area really as a circle, like so, okay, and the other areas. And then here's my main router. And the simplest topology, of course, is for each area to be connected to the campus router in exactly like a star, like that, okay? In which case, all paths are straightforward. If you want to go from some computer here, if you want to go from here to here, you have to go like that. And that's basically all you can do. Okay, that's one kind of abstraction I want to show over here. The second abstraction is this over here, the autonomous systems which are connected in the form of a mesh, okay? And that's, again, I'm going to show over here the autonomous systems drawn like this, okay? And here things are kind of interesting because I have different ways of getting from one place to another, okay? And it's some kind of arbitrary connection. It's not quite arbitrary because each autonomous system has to make an economic decision. Who do I connect to? How much money do I want to pay? What kind of link do I want to have? What do I do? So they have to make their own economic decisions. We're leaving that out of the picture. From our perspective, we just have something that looks like what we call a graph. Okay? And we've seen this a little bit. In drawing this graph, you have to realize that each node over here, though it's just drawn in a circle, really is this whole thing over here. And to be more precise, is this list of subnets that are in that area. Okay, so we really have what we call a list of sort of network numbers, okay, aggregated IP addresses that each belong to this node. Okay, and we're going to ignore all of that and just give each node a simple label like A, B, or C. Okay, and then just similarly, I could number these as 1, 2, 3, 4, 5, 6, 7. Okay. And now I can ask the simple question of how do I get from A to B, how do I get from A to C, how do I get from B to C, etc. Right? In the same way, I can ask questions of how do I get from 1 to 7, okay? And what is the best path to get from 1 to 7, okay? So I've taken all this and shrunk it down and put it over here, so now we can think about it. In particular, what I can do over here is that I can put some weights on these edges. What I can do is I can say this, basically higher weight is worse, so higher weight so I can put weights like 1, 7, 3, 12, 2, 4, 6, I don't know. I just picked some random numbers, okay, some small integers. And now I can say, what's the shortest path to go from 1 to 3? Well, obviously the shortest path is 2 because the other way of getting there is 1 plus 3 plus 7, that's 11, right? So I should take this one, okay? Remember, I can get to 3 not just in this path, but I can also go all the way over and down. I could do that too. I mean, that would be kind of a crazy thing to do, but it might be the shortest path for all you know. I could always choose numbers in such a way so the shortest path in terms of weight was not the one-hop path, but was this path over here. Okay, so we had to be careful to choose these paths, okay, because you can't just pick something and say it looks shortest to me. You have to do some calculation, okay, and that's exactly what these link state and distance vector algorithm are all about, okay, these ways of doing these calculations, okay. So I'm going to take a break in just a moment, but before I do that, I want to make sure everybody gets what's going on, because I'm going to now basically erase all of this, okay, and work with this. But you got to remember that this and this are the same thing. It's not two different things. One of the biggest mistakes people make in studying routing is that they are presented in textbooks with this picture, okay. They look at this picture and they say, oh, right, I understand it. But then when they're confronted with this, they have no idea what's going on because there's no obvious match. You kind of have to make that connection in your brain that this is reality. Okay, this is actually also a picture of an abstraction of reality. This is not reality. This is not actually a router. It's just a piece of chalk on the board. Okay, so let's start with this orange blob over here, okay? I just drew orange blob among all the IP addresses that belong to the Math Center router, which are routed by this, which are reachable by this link. Let's be even more precise, okay? And which are those addresses? Those are the IP addresses which have these prefixes, right? These IP prefixes, okay? Which are the network numbers that we've studied so far. Similarly, for DC, I have a list of prefixes and so on. So this entire thing I'm going to draw as this circle over here, corresponding to some set of IP prefixes. And then the fact that this is connected to this campus router called A over here, campus router called B over here, okay? And that one becomes, this is B. Sorry, I shouldn't call that B. I should call that CR, just to make sure I'm not confusing you. That's CR. And the 2 is the CR1. I'll draw the other one in a minute, CR2. So this is what we're actually drawing. Okay, so we have CR1, CR2, That's A, this is B, this is C, D, E, F, and so on. So, does that make sense? Yeah. In the same way, these things have some structure inside them. Like what is Orion's topology? I don't know. It's private. They don't actually tell you what it is. We don't know what Hydro 1's topology is either. So they have some set of routers connected to each other, okay, in some arbitrary fashion. And we can think of that as being another area. And that's the structure inside this node over here. From our perspective, what is important is the way in which these ASs are connected to each other across inter-ISP links, which is what I've drawn over here. These are inter-ISP links. Okay, let's go back to this whole graph abstraction and to this, to the graphs. Okay, so most people, when they think of routing, they're actually thinking of routing on these graphs. So let's get right down to that and see how to do it. Okay, so we're going to start with this very simple problem. Let's just take this problem right here. Just really, really simple. It's A, this is B, this is C. And the edge weights are 1, 1, and 2. And I want to find the shortest paths. Actually, I'm going to make this 3. I want to find the shortest paths from A to B, B to C, A to C. That's really all there is we have, right? This, if you can solve this, you kind of basically can solve everything else. Okay? Everybody can see this? So remember, this is just the abstraction of that big picture over here. Okay? How do we solve this? So we have two ways of doing it. One's called the distance vector algorithm, and the other is called linked state algorithm. And it turns out that they're sort of the same thing when viewed the right way, but I'll talk about them as being different. Okay? So the way, let's do linked state first, it's kind of easier to understand. The way it works is that each node, so linked state, let's write this down. So we got to assume something. Okay, we're going to assume each node knows it's attached edges and the nodes at the other ends. Okay, and 2, we assume, for now, we'll just assume that links are bidirectional, but we actually don't need this, but we just assume it just for now because it makes it easier. Okay, and link weights are known to I guess I want to basically say that if B says this has a weight of 3, so does C. Okay, they both agree on what the link weight is. It's not like B says my weight is 3 and C says no, the weight is 5. They got to agree on the link weight. Okay, so link weights are shared and common, I guess, of this. Okay, and finally, we have to assume that all node names are global. I don't know if you can read that at the bottom, Donald, but I said all node names are global. Okay? All right, so what I'm assuming is each node knows its attached edges. So B knows it has 2 edges, this one and that one. And the nodes at the other end. So B knows that A is at this end and C is at this end, and these names are global. Everybody knows when I say A, I mean this and not that. It's not like this node says, oh, I call that A, I call that B, and I call this C. No, everybody agrees A, B, and C refer to the same thing. We call this a global namespace, or global in this case address space, which is nothing more than the IP address space, right? Everybody agrees on IP. Remember what I said, IP everybody agrees on, so everybody agrees with these names. Otherwise you're in trouble, right? If people say, no, I call that something else. We assume links are bidirectional, link weights are shared in common, so everybody agrees what this is. And these are actually true in practice. Okay, so it turns out that the way a node knows its attached edges and the nodes at the other ends, because we put it in by hand. Okay, there's these ISP operators sitting there who actually enter these values by hand. So then say I have 5 links, link 1 is this, link 2 is this, the other end is this, all done by hand. Links are bidirectional is almost always the case. Link weights are shared in common, again that's done by kind of, we agree on it. And then all node names are global because it's IP. So if you do this, it turns out that this is what, let's say, node A can do. Node A can create a packet that looks like this. It has 3 fields. The first field is A's name. The second field is a neighbor's name, its own name, it's a neighbor's name, and then the weight, which is in this case 1. And it also has another packet. A says, I have a link to C and the weight is 1. And then that's 2 packets from A. B says, I'm B, my neighbor is A, and the cost is 1. And B says, I'm B, my neighbor is C, and the cost is 3. And C says the same thing. Basically, C says, I have a neighbor called A, cost is 1. I am C, my neighbor is B, the cost is 3. Okay? Do you see how you can make these packets? Once we make these packets, we give them a name. They're called link state packets. Okay, these are link state packets because they tell you the state of the link, because in general, these link weights can change over time, right? It could be that, for example, this link got broken, a backhoe went over the line and cut it. So that means the link weight will go from 1 to infinity, and then the state of the link changes. So A will tell C, hey, that link from A to C, guess what? That's infinite cost. So that's a link state. So we're going to have to deal with that, but we want right now. Let's just look at this over here. Once these link state packets are created, what happens is that they are flooded. Okay, flooding means this. Flooding means that when you get something that's come in on any interface, you send it out on all the other interfaces. Okay, unless you've already done that before. Okay, so you get something, you tell everybody about it, unless you've already done that before. How do you know you've done that before? There's actually a sequence number over here, which I haven't told you about. There's a sequence number like 1, okay, and the sequence number field makes sure that, so A basically increments the sequence number each time it sends out the link state packet. So we know that, oh yeah, we already saw, B says, I already got a link state packet from A sequence number 1, and I told C, if I get another link state packet from A which has sequence number 1, I'm not going to flood it anymore. Okay, so flooding does not require routing. Okay, flooding does not require routing because everybody gets everything. It's a terrible way to send data because everybody gets everything, but it's a great way to send routing messages because everybody gets everything and you're doing it not very often. For example, for link state packets that are inside University of Waterloo, unless there's a problem, in which case you send it quite often, the link state packets send out once every 30 minutes. Okay, so it's not a lot of data to send, and we don't. So flooding is not a big deal when you do it so rarely. Okay, all right. So in this trivial example, flooding is not particularly useful because it's a clique. Everybody's connected to everybody else. But if I took the more general case over here, if I were to take this over here, for example, 3 would create a packet like this. 3, my name is 3, my neighbor is 7, and the link cost is 2. And it would flood it. So let me draw the flooding over there to see how that works. So and let's say the sequence number of this is 24. Okay, so it's the sequence number. It's the source, the destination, if you want, and the weight. Okay, so 3 is going to send it to all of its neighbors like that. Okay, when 1 gets it, it says, okay, I got it on this interface. I'm going to put it on that interface. Okay, and 2 is going to get it, say I'm going to put it on this interface, so it's going to go like this and like that. 4 gets the same packet twice. Okay, it picks either one and sends it out on these two interfaces, and this one gets in from here, and then maybe this goes like that. Doesn't really matter. 6 gets it 3 times. Okay, it's a bit wasteful because everybody gets it multiple times, really, corresponding to these pink arrows going out like so, right? But everybody does get it. And so if the number of edges in the graph is E, whatever E is, then each message is going to travel every edge once and only once. Because once it's been seen, it's not going to be sent back, and it's never going to be sent out again, because we know we already got it from there. So we know that every message only covers each edge once. Okay, so it's not that expensive to do. Okay, the number of edges is not that high. Okay, so but basically everybody gets this packet. Okay, everybody okay with that? Once we get these packets, then it's just a matter of putting the graph back together again. Because what you do is, you basically know that I have an edge A, B, so I have A and I have B, all right, and the edge is going to be 1. And when B knows its neighbors and so on, so basically you can reconstruct the graph simply by attaching the, so there's an edge from C to A, which is 1, and there's an edge from B to C of 3. So everybody constructs this graph in parallel, because you just flood all the link state packets, and essentially you get twice the amount of information. Okay, in this case you're getting the link cost twice. Now for bidirectional links, where the cost is the same in both directions, it's extra. But if you have unidirectional links, or if you have costs in different directions, you'll find out the different costs in different directions in this way. So that's why we do it this way, right? So we get link state packets from both ends. But here is the graph. And what I'm claiming is that by doing flooding, everybody gets the whole graph. Okay, so everybody clear on that? Flooding allows us everybody to get the whole graph independently. Now what they need to do is to compute the shortest paths. Okay, the shortest path from A to B is this one. Shortest path from, sorry, A to C is this one, A to B is this one, and from the shortest path from B to C is this 2-hop path like this. Okay, it's not the 1-hop, it's a 2-hop path that goes like that. And both C and B need to know that. So how do we compute that, right? That's what the question. So I'm going to explain to you how this works. First, I'll tell you intuitively how it works, and then I'll show you the algorithm. Okay, but before I do that, any questions about link state packets and flooding? Okay, so you can imagine how to write the code to generate these link state packets. These are just messages. And you can imagine how you do flooding. Basically, on each interface, you're going to have to just send the messages out. And when you get something in, you look at it and you say, have I sent this already? If not, I'm going to tell everybody else. I'm not going to send it back the way it came. I'll send it everywhere else. Okay. Let me take this one over here, and I'm going to show you the intuitive idea of one way to find shortest paths. Okay. So let's take 3 over here. And what I'm going to do is I'm going to tell you the way to do it. The way you think about it is like this. Imagine there's a big bucket of paint that you drop at 3, and the rate at which it goes across, the number of time steps it takes to cross a link is the weight. Okay, so if it's a 7, it takes 7 time steps to get there. And if it's 2, it takes 2 time steps to get there, and so on, right? So the weight of the edge is sort of how long it takes for the paint to get there. Okay, so well, let's just see what happens, and I kind of have used green to show you the sequence of events. So at time 0, 3 throws a bucket of paint, and what's going to happen is that it's going to get to 1 in time 2, it's going to get to 7 in time 2. So basically I'll just write down node, and then the time, okay, and then the path. Okay, so node 3 gets to E0 and at time 0, and the path is just, self, because it started from 3. Now it got node 3, it got to node 1 at time 2, and the path is 3, 1. It got to node 7 at time 2, and the path is 3, 7. Okay, so we've got these 3 guys taken care of. Let's take a look at this. Okay, this node can be reached, the paint reaches us in many different ways, but we know for sure that the shortest way to get to 7 is time 2, and it can get here in time 3 along this path. Okay, this is already 7. There's no way it's going to get from anywhere out of here to get here in less than time 3, all right? Because I already added 7 over here, and I already added a 2 over here, and 1 over there. Again, it's not going to get to here in time 3. So it's pretty clear that I'm going to get to here. The best way is going to be in time 3. Okay, so node 6, I'm going to get at time 3, and the path is going to be 3, 7, 6. What is the argument I'm using? The argument I'm using is that I know the shortest path to get to anything that's been shaded in green. And if I've already used up more than that to get to somewhere else, it can't be shorter to get there through any other path. Okay, so let me run that argument one more time. So this one was 12 over here, just to show you this. So I got to here in 3 steps. I'm going to write 3 over here, 2 over here. Okay, and I've got to here in 2 time steps. I'm going to get to this one in time 3 as well. Okay. This node 2 in time 3 as well, through this path. And I took 7 to go to 4, so I can't get there in faster than 3. And I took 3 to get here, so I can't get there faster than time 3. So it must be the case that this one, the time is going to be 3. It can't get any shorter than that. And the path to get to node 2 is going to be 3, 1, 2. Okay? Now that just leaves these 2 nodes over here. This node I can get through from 3 plus 6, I can get through 9 along this path. Okay, I can go through 11 on this path. Or actually, let's do this one here because it's a bit closer. I can get through 7 in this way, or I can get 2, I can get 3 here plus 3, I can get 6 along this path. Okay, or I can take 15 along that path, or I can 7 over this path. The shortest path is 6, which is from here. Okay, yeah, I made a mistake on the time, didn't I? Let's see, so yes, the node was 2 and the time was 3, correct. And then the node 4, I'm going to get there at time 6, and the path is going to be 3, 1, 2, 4. Okay, so I got 4 at time 6, and now I got to get to this last node over here. I can take it in time 10 or 9 along this path, and that's basically it. I can get the 10 or 9. The shortest one is 9, which is along this path. So I get to node 5 at time 9, and the path is going to be 3, 7, 6, 5. Okay, so the general algorithm is something like this. I know for sure where I am, that's myself, and I look at my outgoing edges, okay, and I pick the lowest cost edge leading out, which happens to be in this case both of them 1 and 7. So I know that I can't get there any faster because those are the lowest cost edges leading out. If the lowest cost edge was 1 over here, then I pick that, but if they're both the same, I'm going to pick these 2. So I know this for sure, and I know this one and this one because those are the least cost edges leading out, and it can't be the case that I'm going to get there any faster. Okay. Then what I do is I create this kind of blob over here. This blob represents those nodes to whom I know the shortest path for sure. Okay, I know the shortest path for sure, and then I find all the ones that are near 1 hop away from this blob. Okay, so like 4 is 1 hop away from the blob. 3 is 1 hop away. 6 is 1 hop away from the blob. And what I do is that I find the cost to get to these nodes from the blob, because I know the routes inside the blob. So I know I can get here in 2, so I can get here in 3. I know I can get here in 0, so I can get here in 7, I can get here in 3. Okay, and so the least of those, these 2 are the least ones. I can both get there in 3 based on what I know. So I can add them to my blob and add the paths to them like I did over here, 6 and 2. I did it that way. And now I look at this node over here and this node over here. I can pick either one. So I can say I can get from my blob, I know it takes 3 to get here. It's going to take 6 on this path, 7 on that path. And it's going to take 15 on that path. Those are the 3 ways to get to from the blob, okay, to this node here. And the shortest one is this. So I pick this. The blob is expanded. I get node 4 and then node 5 similarly. Okay? And this algorithm, which is sort of, the blob that ate everything algorithm, was invented by a guy called Dijkstra. So it's also called Dijkstra's algorithm, but I prefer to call it the omnivorous blob algorithm or the bucket of paint algorithm. And that's what it is, okay? And the writing the code for it is pretty much what I did over here. You have, this is what you call as the connected component, which is no connect component, which you know everything, you know the truth about it. And then you find the adjacent neighbors and you find the shortest paths from your component to the shortest path. You pick the least of them and then you add that and you sort of slowly grow what you know, and so that at the end you know everything. And each node can do this in parallel. Why? Because each node has the link state packets, which are called through flooding, and so everybody gets a routing table. So how do you use a routing table? It's very simple. So let's say 3 wants to decide to send a packet to 5. So I want to send a packet to 5. It says, okay, to get to 5, my path is 3, 7, 6, 5. So it says, I really have to send it to 7. I'm going to send it like this to 7. Okay? 7 says this packet is going to 5. And similarly, it's computed that its shortest path is going to be 6, 5. Okay? And it will turn out that all shortest path tables are consistent because everybody has the same state. So 7 is going to give it to 6, 6 will give it to 5, and it gets there. Okay? As long as everybody gets the same link state packets, everybody has a consistent view of routing. But that may not always happen. If a link state packet gets lost or corrupted or gets delayed or something, then different people will have different views of the routing table, of the graph. If they have different views of the graph, they'll compute different routing tables, and then you'll get routing loops because people have an inconsistent view of the world. Okay, and that's how you get routing loops. Okay, so what I'm claiming here is that this algorithm, the omnivorous blob algorithm or Dijkstra's algorithm, allows you to compute routing tables, and in fact this is what we use, or a variant of this is what we use in the area. So inside this one, inside University of Waterloo, okay, there's a protocol called Ospf, and that stands for Open Shortest Path First. And Open Shortest Path First algorithm is exactly this link state algorithm. Okay, and so open means that it's an open specification. It's not a proprietary thing. Anybody who wants to implement it. You can sit in your garage and type the code for Ospf and sell it if you wish. Nobody's going to stop you. Then you have shortest path first. That's Ospf. Why is it shortest path first? Because we take the shortest paths, and then we kind of order them, and then you find the first way to, basically we're choosing the next hop based on the shortest paths. So it's called open shortest path first. So every half hour or so, okay, it's a timer, every node will broadcast or flood its link state packets. And all the nodes are doing it at the same time, more or less. It's slightly jitter to prevent, bursty. But so they're receiving all of these packets, and they propagate in 5, 10, 20 milliseconds, whatever time it takes. And when you've got all the packets, you create this topology over here, graph, and then you run Dijkstra's algorithm, and then you say, okay, here's a new routing table. There is a change. There is a caveat. This routing computation is triggered also by sudden changes. So if there is a break, a link break, what will happen is that the link state packet, for example, let's say this link breaks. A knows about it, for example, or B knows. They both will know. Actually, they both will detect that the link has gone down. So they will both say BA infinity, AB infinity. When this happens, what's going to happen over here is that this link is not going to be used at all. What will happen is C is going to get those new link state packets. It's going to construct a graph which looks like this. C, A, B. So A knows not to use the link, obviously, because it's broken, so it's going to give it to C. C says, okay, I'll give it to B, and B does likewise, and it works. Same thing over here. Let's say any of these links were to break, if this link over here were to break, well, that link isn't used at all, so it's not a big deal. Let's say this link were to break. what's going to happen is that 3 would know that 7 has gone down, and any path, so 1 would use 3 to get to 7, for example, in this case over here, because 1 is going to use this path of length 4. So 1 would see this link has gone down, and so the paint will never spread down here. Right? It's never going to go down here. It's going to use some other path. Maybe 1 is going to go 3, 4, 5, 6, 7, something like that. Okay, it depends on what the weight is. So, but 1 needs to give it to 3, for example, and so on. So we would basically, every node would compute the consistent shortest paths that are dependent on this link going down. So your link goes down, immediately you tell everybody, you know, and then everybody is going to respond to that. With Ospf and with most routing protocols, the way this described, you know, when we talk about an introductory class like this, we just assume that first the link weights are constant, but that's not true. The link weights do change, and if the node is persistently congested, the weights will go up. Okay, but we've got to be very careful because we can get into some problems. I mean, just look at this problem over here. Let's say I have 2 paths from A to B, and the paths are going to be cost sensitive. So I put, let's say all the traffic is going on this one here, so it makes this link cost heavy. So all the traffic will go on the lightly loaded path. So it's going to go here, and then that's going to get heavily congested, and then it's going to go there, so it's going to have this flapping, route flapping. It's like saying you're going to go to Toronto either on Route 7 or the 401. 401 is backed up, it's on the radio, so everybody goes on Route 7 and that backs up. But actually you see this in practice when you're on the 401 and you have the collector and the express lane, and you have a big sign that says express lanes are congested. Okay? If you are following the signs, you'll go on the local lanes, in the collector lanes, right? And everybody's going to the collector lanes, so express lanes will be uncongested. So if you're really smart, when it says express lanes are congested, you should go on the express lanes. But if everybody else is smart like you, it's not a good idea. Okay, so you have to be randomly smart, you know. So on Mondays, Wednesdays, and Fridays, you're smart, and on Tuesdays, Wednesdays, and Thursdays, you're dumb, or maybe so smart that you're dumb. Okay, it's hard to tell the difference anymore. But that's the route flapping problem, and that happens in real life all the time. You know, you're driving in at the airport, it says collectors are busy. You know, what do? You really don't know. You know, should you pretend everybody's dumb, or maybe it's in a Friday night they're all dumb, but Monday morning they're all smart, you know. This is game theory. Okay. Okay, let me take a break, and then after that we'll continue with the distance vector algorithm. Remember, this is the link state algorithm I talked about just now, and Ospf. Okay, so let's look at distance vector, and actually it turns out distance vector is much easier to explain, so I'm going to do it. It doesn't require such a complicated story. The assumptions for distance vector are pretty much the same, so I'm not going to change them. However, what's being sent out is different. Okay, what's being sent out is what's called the distance vector. And the distance vector looks something like this. It says it has, the message is your own node name, okay? And it has the distance to each other node. So this node, distance to node 1, distance to node 2, this is node 3, and so on until the last one. You know? Remember, everybody has a common name, so we can kind of view all of these as having some sequence, and so you do the distances to kind of all of them. So let's do it for this example over here, make it easier to understand. So I'm going to erase the link state packets and show you the distance vector packets. What do distance vector packets look like? So basically, A says I'm A, and my cost to B is 1, and then my cost to C is 1, okay, and then B says my cost to A is 1, my cost to C is 3, and then C says my cost to A is 1 and my cost to B is 3. So this little thing, the vertical bar, just means I have 2 kind of subfields in there, okay? These packets are not flooded. These packets are not flooded. Instead, they're sent to the neighbors only. Okay, so A will receive a distance vector packet from B and from C, and C will get it from A and B, and so on. What happens when you receive a distance vector packet is that you can figure out what's going on. So A, when it gets a distance vector packet, so A doesn't know of the link from B to C. It doesn't know that, okay? And similarly, B doesn't know the link from A to C. B only knows that it has, it knows that, so it knows that this, okay, let me actually draw this over here. So let's draw, let's draw what B knows, okay? Okay, at time 0, B knows that there's a node that's called A, and the cost to get to A is going to be 1, and it knows at time 0 that there's a node called C, and the cost to get to C is 3. That's all it knows, okay? And so the initial distance vector packet that B is going to send out is going to say something like this one over here, right? This is the initial distance vector packet from B, okay? Now what happens is that A knows this at time 0. Okay, that's all it knows at time 0. It sends this message to B. When B gets this packet, it says, hey, wait a minute. I know that I can get to A in time 1, and A says that it can get to C in time 1. So that means that I can go, so B receives distance vector packet from A. Okay, at this point, let's say at time 1, B says I can get to C at cost 2 through A. Okay, why? Because it got this packet over here. So B says, if I can get to A in 1, A can get to C in 1, then I can get to C in cost 2, and I have to go through A. Right? Do you see what's going on in there? And that's all it needs to get the right routing table. Same thing happens with C. C knows in the beginning of time that it can get through A in 1 and B in 3. When C gets a distance vector from A, C updates its local state to say, I can get to A in 1. A tells me it can get to B in 1, so I can get through A. I can get to B through A, it costs 2. And it updates its local routing table. And that's it. Okay, works for more complicated topologies, and just to give you a snapshot of this, okay, so let's say this is A, B, C, D, and the costs are 1, 1, 10, 10. I'm not going to draw each step, okay, but you can see that the shortest path from A to D is going to be of 2 through B. So in the beginning, A only knows that it has a cost of 1 to get to B and 10 to get to C. Okay, but B knows it has a cost of 1 to get to D, 1 to get to A, and so on. So B's initial distance vector is going to say I have a cost 1 to D. All right. A's initial distance vector is going to say I have a cost of infinity to get to D, because I have no way, I don't even know I can get there. When A gets the distance vector from B, it determines that it can get to D in time 2 through B. So it says, oh yeah, I'm going to go this way. It also finds out from C that it can get to D from C at a cost of 20, but the lower cost is through B. So it's going to choose to send all its packets for D through B rather than C. Okay? So basically, when you get a distance vector, you say, have I discovered a shorter way to get to some destination based on what the distance vector tells me and my own current state? If it's true, I'll update it. And there you go. Okay, and that's a distance vector algorithm in a nutshell. And that is used in inter-AS routing. Okay, in inter-AS routing, what happens is that we actually use a slightly modified version of this called the path vector algorithm rather than distance vector algorithm. What happens is that instead of having the distances, we actually say this is the cost to destination plus path to destination. And the reason we do that is because we want to know what path was used to get there. So in the specific case, B tells A in its distance vector and its path vector, okay, or let's actually use another node over here. Okay, so let's say B discovers that it has a cost 2 paths to E. So B will tell A, I can get to E through the path BDE at cost 2. Okay, and let's say C can get there at time 2. So C will tell A, I can get to E at cost 2 on the direct hop CE, and A will say, okay, if I go through B, I'm going to be costing me 1 plus 2, that's 3. If I go through C, it's going to cost me 10 plus 2, that's 12. So I want to send through the path A, B, D, E. So the same kind of path that we discovered in linked state algorithm is also achievable through distance vector by exchanging these paths. And the protocol that we use is called the border gateway protocol, which uses this. And this often called BGP. And the reason is because if you remember when I drew that picture, I said, inside each AS, the edge nodes are called the border gateways. And this is what's spoken by the border gateways to do inter-AS routing, long distance routing. And we use these paths. These paths allow us to avoid routing loops, because when you see a path, you say, yeah, sure, I don't want to go to the same path twice, same node twice. So we avoid routing loops using paths. With distance vectors, there are cases where you can get routing loops, and I won't get into that, how that happens. It's it's well described, and you can look it up, but path vector avoids these loop problems, and that's why we use path vector as BGP. There's a lot more complexity to routing than what I've touched upon over here, but it's not something that I want to go into. So to summarize what I said so far today, we need to remember that routing is hierarchical. We have sort of routing inside your LAN, you have routing in your area, and you have routing sort of in your campus with multiple areas, and then you have routing between autonomous systems. Inside a LAN, it's broadcast, it's easy. Between areas, we use Ospf and linked state, and within across areas, we use BGP. So that's basically how it works. And the two algorithms are distance vector and linked state.